Yeah, you can go ahead.
Great. So, yeah, okay. So let's remember our original goal was to define what it means for a function on natural numbers to be computable. We spent a bunch of time seeing this definition of primitive recursive and proving that a bunch of things are primitive recursive. But then I just told you that it doesn't actually define computable because there's some computable functions that grow too fast to be primitive recursive. However, if you add one more operation to the definition of primitive recursive, you do get a formal definition of computable. But to explain that one more operation, I need to talk a little bit about partial functions. So a partial function is just a function that's not defined everywhere on its domain. So in other words, a partial function is, say from n to the k to n, is a function whose domain is a subset of n to the k. So it could be missing some elements of n to the k. And often we'll write f of n1 through nk with an up arrow. This means something different than before. It means diverges. Or sometimes f of n1 through nk equals up arrow to mean that that input is not in the domain. On the other hand, sometimes you'll see people write f of n1 through nk with a down arrow to mean it is in the domain. So a partial function is a function that may not be defined everywhere, and we have this notation to say when it is or isn't defined. And now I'm going to define this operation. So for any function f, mu f is the function defined by, so it's a function from n to the k to n, and mu f of m1, or let's say n1 through nk. This is the least let's say m such that f of m n1 through nk is equal to 0, but it's possible that no such m exists. So if no such m exists, this function is not going to be defined. And so actually this is not really a function, but rather a partial function. And that's why I defined partial function. And likewise, we can actually let f, instead of just being a full-fledged function, also be a partial function. And this operation is sometimes called unbounded search because there's no a priori bound on how large little m could be. And it's also sometimes called minimalization because you're trying to find the smallest m that satisfies this property. So we're going to expand the definition of primitive recursive to allow this kind of unbounded search, which in some sense corresponds to like expanding our programming language to allow like while loops or recursion or something like that. First, maybe I want to say that primitive recursion and composition / substitution still make sense even when the functions involved are just partial functions rather than total functions. So in other words, if f and g are partial functions, let's say from just natural numbers to natural numbers, we can still define their composition. And it's equal to f of g of n if g of n, if n is in the domain of g, and g of n is in the domain of f. And it just is not defined otherwise. So in other words, as long as both g of n and f of g of n make sense, then this acts like the composition normally does. In other words, and otherwise it's just not defined. So composition still makes sense. Primitive recursion also, you can check, still makes sense. So with that in mind, we're going to define the class of general recursive functions, and I'll abbreviate it sometimes GR, as the smallest class of functions which contains all primitive recursive functions. And which is closed under three operations. The first two are the same as from before: composition / substitution and primitive recursion. But now we add this one extra operation, which is minimalization or unbounded search. And that defines the general recursive functions, and that is the class of functions that is claimed to be the computable functions. Okay, so that's the definition. Now I want to say a little bit about that. So Alonzo Church, I think Gödel originally defined this class of functions, but Alonzo Church was the person who first claimed that it corresponded exactly to the intuitively computable functions. So the Church-Turing thesis, which I think Alonzo Church first stated, was that a function is computable in the intuitive sense if and only if it's general recursive. So the Church-Turing thesis is not some kind of theorem that can be proved or something like that. It's more of a sort of just assertion about the world. So like we have some kind of intuitive notion of what computable means. And this is saying this formal mathematical definition does capture that. But that's not something you can prove because the intuitive notion is just an intuitive notion. So Alonzo Church made that claim. And I guess Gödel at the time was not convinced this was correct. Basically, the definition of general recursive, it just seems a bit arbitrary. It's pretty, you can convince yourself that everything in it is computable, but the troubling question is maybe, how do we know we haven't missed anything? So that was Gödel's objection. And this is where Turing came in. So Turing, maybe not quite in his words, but basically said the definition of general recursive function is kind of strange. So instead, he gave a definition that is closer maybe to the intuitive meaning of computable. Then he analyzed like why that should correspond to the intuitive notion of computable. He proved that it was equivalent to Church's definition, and he additionally proved a bunch of other stuff. So as I said, he defined something which is now called Turing computable. Of course, he didn't call it that. He gave an argument for why it's correct, and he proved that it's equivalent to general recursive. And apparently, Gödel was then convinced that this was the correct definition. So Turing's argument was maybe more convincing on these sort of intuitive grounds. So now I'm going to try to describe what Turing computable means and briefly mention like why is it equivalent to general recursive. So what was Turing's definition of computation? He said, imagine some sort of machine, and this machine has an infinite tape of paper divided into squares. And each square has written on it either a 0 or a 1, or it's just blank. And additionally, there's this sort of machine that moves along the tape, which he called a head. And at each step, it can move either left or right along the tape. It can read what's written in the current square of the tape, and it can overwrite that square with either a 0, a 1, or it can erase it and leave it blank. Also, you can store a finite amount of information in the head. So the head has some finite memory, and at each step, it can decide what to do, not just based on what square it's looking at, but also what's currently in its memory. So at each step, it will decide what to do based on the contents of its memory and the contents of the current square. And people, I guess, have even tried to construct some sort of actual physical Turing machines of some sort. So you can see a picture of that at the bottom. So that's the idea of the machine. And how does this actually give you a function from natural numbers to natural numbers? Well, the idea is at the beginning of the operation of the machine, we write the input on the infinite tape. So suppose, for instance, that the input was the numbers 1, 2, 3. What we might do is, starting at the point at which the head is pointing, starting with the square that the head is pointing to initially, we'll write a 1, and then a 0 to indicate the end of the first input, and then 2 1s to indicate the next input is a 2, and then a 0 to indicate that's ended, and then 3 1s to indicate the next input is a 3, and then maybe we'll leave the rest blank. So again, this 1 corresponds to a 1, these 2 1s correspond to a 2, and these 3 1s correspond to a 3. And the fact that there's blanks after and before mean that that's the entire input. Next, there's some particular state of the Turing machine, which is we call the halting state. So if the contents of the Turing machine's memory is a big H, then we'll just assume that the Turing machine is ready to stop. And if the Turing machine's memory ever enters the state, then we'll stop and get the output, and that will be the output for our function. And how do we get the output? Well, we look at where the head is pointing currently, and we look at the consecutive ones to the left of that, and however many of them there are, suppose there's n ones, that will be our output. So in this case, the output would be 3, because there's 3 ones in a row. So that's how you can define a function from a Turing machine. You write the input for the function on the input tape, you let the Turing machine run. When it stops, you get the output from the tape, and that's the output for your function. Of course, it's possible the Turing machine will never stop, will never enter the halting state, in which case this input has no well-defined output, so we're dealing again with partial functions. So that's the definition of the function computed by a Turing machine. And what's the philosophical justification for why this corresponds to the intuitive meaning of computable? Well, we should imagine that a Turing machine somehow corresponds to like a person actually doing computations on pen and paper. So the head of the Turing machine is like some person, and maybe holding a pencil because they can write stuff and erase stuff. And the contents of the memory of the head of the Turing machine is like the contents of that person's brain. And the infinite tape is actually just like some large supply of scratch paper that they're writing on to keep track of their work. And the halting state is the person's brain entering, having the thought like, I'm done. Okay, so here I've drawn this little picture. And maybe I can comment that originally, I think there's some things about the picture I've drawn so far that are not completely convincing. Like, you might think it's weird that we write the answer on the same tape that we got the input on. So originally, actually, Turing specified that there's multiple tapes. And maybe one tape has the input, one tape is for the sort of scratch work of the machine, and one tape is for writing the output. You might think that's more natural and corresponds more to the intuitive notion of computable. it turns out not to matter. You can show that all the definitions are equivalent. And the other difference originally was that you weren't allowed to only write 0 and 1, but you could have any finite alphabet, and you could write any symbols from that alphabet. So you could have the alphabet A through Z, and you can write on the tape any of the letters A through Z, or something like that. And the philosophical justification, again, is just supposed to be like, what are you actually doing when you as a person compute something? You're sitting there, you have some thoughts in your head, you have paper in front of you, and in each second, you can change the thoughts in your head, you can replace a symbol on the paper in front of you, and that's pretty much all you can do. So this was Turing's analysis. Now let's write a slightly more formal definition of a mathematical definition of a Turing machine. So mathematically, a Turing machine consists of a finite set, let's call it Q. And what is this finite set? This is the set of possible states of the memory of the Turing machine. And secondly, we have a function, which is usually called a transition function. Telling us basically what the Turing machine will do at the next step. So it takes the contents of the Turing machine's memory and the contents of the current square, which could either be 0 or 1 or blank, and it tells us what the Turing machine should do at the next step. So first, didn't mean to write that. So first, what the Turing machine's new memory state will be, and second, what action the Turing machine will take. So some of the possible actions are it could move to the right, move to the left, it could enter the halting state, it could replace the contents of the current square with a 0, with a 1, or with a blank. So then the R means move to the right by 1 square. The L means move left by 1 square. Sorry, I guess I actually shouldn't have included this halt, because what I said before is that it's the halting state is part of the set of possible states of the Turing machine's memory. So H is actually part of Q, not part of set of actions. Okay, 0 corresponds to write a 0 on the current square. And so on. So again, the transition function just tells you, based on the current state of the memory and the current contents of the square that we're looking at, what should the Turing machine do next, and what should its memory look like next? So that's the formal mathematical definition of a Turing machine. You could also write down a formal definition of the function computed by a Turing machine. Okay, and then I want to mention, so I said before that a function is general recursive if and only if it's Turing computable. So if and only if there's some Turing machine that computes it. And if you want to prove this in detail, the proof in some sense isn't so hard, but it's got a lot of details, and it takes a long time to go through those details. So I want to describe the main ideas of the proof without necessarily going through the whole thing. So the basic idea of the proof is you can think of all these models of computation, including both general recursive functions and Turing machines and so on, as kind of like weird programming languages. And what you need to do to prove that they're equivalent is become a good enough programmer in each programming language that you can write a compiler for the other programming language. So let me write some of that down. You want to think of general recursion So think of general recursive functions and Turing machines as two very weird programming languages. Then you need to learn how to program in those programming languages. And finally, write a compiler from one to the other. Okay, so maybe this is not clear. I'm not clear what this means, and maybe you don't know what compiler means. But the idea basically is, yeah, you need to build up a lot of practice, like to build up a lot of functions that you know are computable in each model until you can simulate the other model computation. So let me say in slightly more detail, what is the proof sketch of the sort of forward direction of this? So if a function is general recursive, then it's Turing computable. Well, to prove this, we can show that the set of Turing computable functions contains the basic primitive recursive functions So remember, those consisted of the constant functions, the successor function, and the projection functions. And is closed under those operations that we saw before. So it's closed under composition/substitution, primitive recursion, and minimalization. And if you can show that, then you've shown that the set of Turing computable functions must contain the set of general recursive functions, because the set of general recursive functions is the smallest set that contains those basic functions and is closed under those operations. So how do you do this? Well, you just need to write a lot of Turing machines. So let's do at least one example to kind of show how it works. So say we want to show that the projection P32 is computable by a Turing machine. So remember, this is the function that takes as input 3 numbers and gives you the second of those numbers. So if you recall how I said that the function computed by a Turing machine works, if you suppose that this is the input, so the input is 2, 1, 3. So the output is supposed to be the number 1. It would be enough if we could get the head to move over here. Okay, so if you can move the head over to there, then you remember the output was just, we counted the number of ones, consecutive ones to the left of the head, so then the number of consecutive ones would be 1. So we need to write a Turing machine that will just sort of like move past the first block of ones and then move to the end of the second block of ones. So what is that Turing machine going to do? Well, let's kind of write some sort of description of what it does and then try to write down an actual Turing machine. So what we need to do is, well, the current square is 1. We should move to the right. That will bring us to the end of the block of 1, the first block of ones. We should then move to the right again to enter the second block of ones. And then again, we should move to the end of the second block of ones. So while the current square is 1, after that, we're pointing at the 0 after the second block of ones. So then we should move back 1 square to the left to be pointing at the last 1 in the second block of ones. So if you wanted to actually write down a Turing machine, one way to do this would be to use as the memory, I guess, 3 states, the halting state, and then A and B, which A is going to correspond to like when we're in this phase, and B is when we're in this phase. So the Turing machine will just remember, am I currently in the first block of ones or the second block of ones? And what's the transition function? Well, I won't write the whole thing, but the relevant parts are when we're still in the first block of ones and we see another 1, we should keep the same memory and move to the right by 1 square. When we're still in the first block of ones, but now we see a 0, that means we're at this first 0. So we should remember that we've hit the end of the first block of ones, so we'll just switch to the B state, but we should move to the right again. That's like this move right. Now, if we're in the B state and we see a 1, then we should just move to the right, because we want to move to the end of that block of ones. But if we're in the B state and we see a 0, that means we've hit the 0 after the second block of ones. We should move back over to the left and enter the halting state, because we found the end of the second block. So we'll do this. So in this function, actually, it's not necessary to change any of the contents of the tape. We just have to move around on it. But anyways, that's how you can compute this projection function. And you can figure out how to compute any of the projection functions in a similar way. So now if we go back here, what did we need to do to show that general recursive implies Turing computable? Well, we need to show it contains constants. That part is actually relatively easy. Then successor function, that part is also not too hard. Projections, we've just done that. And then you need to show it's closed under composition, primitive recursion, and minimalization. Those are somewhat harder, so you need to write much longer Turing machines. But in the end, you're just doing the same kind of thing. Like, we've become a programmer in the programming language of Turing machines, and here's one little program we wrote in that language. So how about the other direction? We want to show that a partial function is general recursive, if and only if it's Turing computable. So we want to show, suppose a function is Turing computable, we want to show it's general recursive. How does that work? This is maybe a bit more complicated to describe. The general idea is something along the lines of the following. We want to pick a way to represent finite sequences of natural numbers by single natural numbers. In other words, we want to pick an injective function and I'll maybe explain this notation in a moment, but from the set of finite sequences of natural numbers to the natural numbers, and that will allow us to think of a finite sequence of natural numbers as just a single natural number. So that's the first step. Maybe it's not clear yet why that's a helpful step to take. So the second step is you want to find general recursive functions for manipulating sequences which are represented in this way. And then finally, if we have a fixed Turing machine T, let's say, we want to show that the function computed by T is a general recursive function. So we want to write a general recursive function or maybe I should say find rather than write. F, which does the following. It searches for a number M which represents a sequence, which is like the entire sequence of what the Turing machine is doing. So it searches for number M which represents a sequence corresponding to the sequence of states of the Turing machine T. So each element of the sequence will correspond to actually another sequence, which encodes both like the current memory state of the Turing machine and enough of the tape to check the entire operation. So basically, this function f is looking for a number m, which represents the sequence, which is a valid sequence of moves according to the transition function of the Turing machine T. So sorry if that's a bit vague. Once you build up enough ways of working with finite sequences of natural numbers, this part is not super hard to do, although a bit tedious. This is what I mean by you kind of need to become a programmer in the language of general recursive functions. So let me now just say a little bit about how you can represent sequences of numbers as single numbers in this way. So first, let me make a definition. This terminology used before. N star, by that I mean the set of finite sequence of natural numbers, i.e. the set of N1 through Nk, such that K is a natural number and N1 through Nk are natural numbers. And let's consider the injective function from finite sequences of natural numbers to natural numbers defined by the sequence N1 through Nk gets mapped to 2 to the N1 plus 1 times 3 to the N2 plus 1, and so on, all the way through pk to the nk plus 1, where pk is the kth prime number. So the idea is we encode the sequence of natural numbers as the exponents of the prime factorization of some number. And then you can check that the following functions are all general recursive. Actually, I haven't written them yet, but they're not even just general recursive, they're actually all primitive recursive. So first, maybe the function that, and let's maybe call this function big C. that sends a finite sequence of natural numbers to a natural number. So first, the indicator function of the range of C is primitive recursive. So in other words, the range of C is a primitive recursive set. Second, the function that sends a number k to the kth prime number. Third, the function that sends a number n to the least, or sorry, not least, the largest k such that the kth prime number is a divisor of n. So in other words, if you were thinking of representing sequences of numbers using the prime factorization of some other number, this third function is telling you the length of the sequence. And fourth, a function that takes n and k and tells you the exponent of pk of the kth prime in the prime factorization of n. So this is essentially telling you the kth element of the sequence encoded by n. And showing that all these things are primitive recursive is not so much harder than showing that the earlier functions we saw are primitive recursive. So basically, you could kind of continue what I was doing earlier and build up more and more functions as primitive recursive, and then you could eventually show that these ones are primitive recursive. And then to go back to here, how do you finish? Well, again, you would write this general recursive function, which has a single use of unbounded search. So that's why we sort of needed to add unbounded search to the language to make it complete. And what does that instance of unbounded search do? It looks for a number n that codes a sequence which says, like, here's what the Turing machine was doing in each step, and checking that that sequence actually does code what the Turing machine was doing at each step. That's primitive recursive. So you have like a single use of unbounded recursion or unbounded search together with this primitive recursive checking that it encodes a sequence and checking that the sequence is following the rules of the Turing machine. So again, maybe sorry that I didn't go into more detail about that. It's the kind of thing where if you go into detail, it takes a while and can be a bit tedious. And at the end of it, you realize that it was sort of obvious. But if you don't go into detail, sometimes it seems very mysterious and like it not convincing why it's true. So yeah, I guess I ended up finishing a little faster than I anticipated. So that's the end of the material I have prepared right now. And I think this picks up again next Sunday or Monday or something.
Okay, thank you, Dr. Lutz. Does anyone have any question? If not, our next session is going to be the first lecture of Introductory Set Theory by Junle Go. It is on Thursday, 4 p.m. to 6 p.m. UTC. It will be Thursday, 12 a.m. on Malaysia time, but it's 4 p.m. to 6 p.m. UTC, so you can check your Google Calendar to convert to your own local time zone. Okay, so if there's no questions from the audience, I think that should be all for today. Thank you, Dr. Lutz, for your nice lecture. And I guess we will see you guys on the next session.
It looks like somebody asked a question in the chat about the recording.
Hang on. Can you access the recording somewhere else? Yes, we will save the recording and we'll find a way to make it available. Thursday or Wednesday? It is Thursday. So hang on a second. February 9th. Sorry, so my mistake is on Wednesday. Yeah. Okay, so it is on Wednesday, February 9th, 4 p.m. to 6 p.m. UTC, UTC time. Okay, and yes, so let me repeat for the recording. I will find a way to make it available through the organizers of this event, and yeah, we'll make it available soon. Any other questions? Yep, someone said they enjoyed the talk, and thank you. Okay, so let's wait a bit more if there's any questions. Yeah, so seems like no other question. So yeah, thank you again. I also enjoyed the talk, Dr. Lutz. So see you in the next class. And thank you, everyone. Thanks for the speaker and the participants.